It took longer than I'm willing to admit to build this car. Mostly because we were really bad at it at the beginning, as shown by this next clip.
All right. So, we put these wheels on this axle here, and then realized that these two things need to go here. It's a clear problem. This is how we want this to look. Something like that. That can't happen anymore.
So that stupid looking thing with the white wheels was the original prototype, and yeah, just nothing about that worked. But basically, that was the start. For a while, the big problem was we couldn't figure out how to get the axles to rotate really very well. But we figured out just to ream the black holes in the little frame rods. It took us a pretty long time to figure that out. And then the axle could rotate. And then we had a frame that could move if you pushed it. And then we just had to figure out how to attach the mouse traps. So we tried glue for like a long time, but like the wood glue somehow just never worked. So eventually we just used rubber bands to just hold the mouse traps down, and it actually worked really well. The frame was like the perfect width for the mouse traps. So then it was like almost good, and the cable ties worked well for the lever arm, which was too short, but that's another problem. And then we just had to attach the string. The string was pretty simple, so tied a simple knot over the dowel. And then, we were supposed to use some kind of loop back here, I think, but like, we didn't really know what to do with that, so we kind of figured we could just coil it ourselves, and it worked fine, I think, for the most part, except for when I went backwards twice. And then, another problem was the wheels. They were like jamming up against like the frame rods here, and you wouldn't really rotate. So we just used rubber bands like this to hold the frame rods like closer together. They wouldn't spread out. And then wheels could like rotate better. Did that on both sides. And then another big problem was the car wouldn't start. Yes, that was a big problem. But we put rubber bands around the outside of the back wheel so we could have some traction with the ground, so we could actually get started. Didn't need to do it with the front wheels, that would just be more friction, but doing the back wheels helped to get started and get going. I think CDs probably would have been less friction as the other group did, which was pretty smart. And a longer lever arm would have been good, but overall, yeah.
Alright, here we have the data for 3 trials. We have distance in meters and time in seconds. So the first thing we did was find the average velocity of our car as it traveled the given distance. So we took the average velocity of each trial, which is right here in meters per second, add them up, divide by 3 to get 1.501 meters per second. So that's our average velocity of the car. And the next thing we have is final velocity, which given by the data table from the motion detector, we have a max velocity of 2.52 meters per second over the 3 trials. That's an average. So the impulse is going to equal m delta v, because impulse is change in momentum, and the mass of the car does not change. It's velocity that changes. So the mass of the car is 0.14 kilograms, and the change in velocity is going to be the max velocity, 2.52 meters per second. And when we plug that in, we get 0.3528 kilograms times meters per second. Alright, and that's going to be the impulse of this car. And lastly, we have acceleration, which is going to be the max velocity over time. So the average time is going to be these 3 numbers added up and divided by 3, which is 8.063, and the max velocity is 2.52. This is meters per second. This is seconds. So then when you divide those, you get an average acceleration of 0.313 meters per second squared.
Okay, go.
3, 2, 1, go. Damn it.
That was really complete and utter.
Welcome, class, to my physics section of the explanation. In our calculations, we said that friction was negligible, yet friction was essential to the car gaining velocity as it gave the wheels traction. This traction, created by the rubber band covered wheels, allowed for torque to be done on these wheels by the string and thus beginning motion. The lack of friction in the front wheels allowed for the car to glide once it gained enough kinetic energy to accelerate forward. Friction was essential to the car moving forward as it constituted the traction that allowed the car to rotate its wheels and effectively convert the elastic potential energy to kinetic energy. The negative friction accounts for the conversion to thermal energy and a decrease in the velocity and distance of the mousetrap car. The less friction that does negative work on the system means a greater change in distance.
Compared to other cars in our class, our car was similar into 2 out of the 3. Brianna's group's car was similarly constructed using the same rods and wheels as ours, but the difference between our 2 cars was that we used 2 mousetraps instead of just 1. This double mousetrap design gave our car more elastic potential energy and helped the car travel further by converting this into more kinetic energy. Our car also had a longer lever arm, increasing the torque and speed of the wheels on our car. Compared to Amanda's group's car, we had a higher quality mousetraps, which gave our car more force and therefore more power. Despite their lever arm being longer, the increase in the force of our mousetraps had a larger impact on the distance the car traveled.
Compared to the last group, our car was distinctly different as they used less mousetraps, but their wheels were more aerodynamic, lighter, and larger in radius, which gave them more distance. They went farther because they had a better power-to-weight ratio, and their bigger wheels allowed for more translational motion rather than rotational motion because their rotational inertia was greater. All of this means that this mousetrap car traveled a farther distance than us.